Whenever the topic of AI's massive energy cost comes up, we're almost always talking about one thing: training. That colossal effort it takes to build a model like GPT-4. But here's the thing, that's only a tiny, tiny fraction of the story. The real energy bill, the one that's running 24/7, comes from something we do all the time, just having a conversation with an AI. And what we're about to dig into is going to completely change how you think about every single prompt you type.
90%. Just let that number sink in for a second. According to our report from Amazon Web Services, that's how much of an AI model's entire energy lifecycle gets used up after it's already been built. Yeah, we're talking about the power it takes just to answer our questions. And it is a staggering amount.
So, if training is just a one-and-done cost, what in the world is causing this huge continuous energy drain? Well, it all comes down to a single word: inference. It's the technical name for what happens every single time an AI gives you a response, and frankly, it's the hidden engine driving AI's entire environmental footprint.
This slide breaks it down perfectly. Think of training like building a gigantic, complicated factory. It's a huge, one-time investment of energy and resources. But inference, that's actually running the factory. 24 hours a day, 7 days a week, for millions of us. Every question, every sentence it generates, that's keeping the lights on and the machines humming. And as you can probably guess, that cost over time just completely dwarfs the cost of building the factory in the first place.
But of course, it gets even more complicated. See, not all these factories run the same way. The first layer we really need to understand is the software that's actually running the AI, what's called the inference engine. And this is where things start to get really interesting.
So the inference engine is basically the AI's operating system. It's the software that dictates how efficiently that model spits out a response. And you can have different kinds. You might have an engine that's built like a drag racer. It just explodes off the starting line, but it burns a ton of fuel. Or you can have one that's more like a hybrid car. It takes a little longer to get going, but once it's cruising, its fuel efficiency is just incredible. So which one do you choose?
Well, let's look at the setup race. Just getting the engine warmed up and ready. Engines like Transformers and DeepSpeed are blazing fast. They are ready to go in under 3 seconds. But then look at TensorRT, LLM, and VLLM. They're taking over 30, even close to 50 seconds just to get started. These are definitely our slow-starting hybrids.
But and this is a huge but, when it comes to the actual journey of generating thousands of words under a heavy workload, the roles completely reverse. Those slow starters, VLM and TensorRT-LLM, are unbelievably more energy efficient. That deep green on this heat map tells the whole story. They use just a tiny fraction of the energy per word compared to the fast starters. Our drag racers? They run out of gas really, really fast.
Okay, so you're probably thinking, easy. Just pick the right engine. Well, not so fast. It's not quite that simple. The next layer of this puzzle is the AI model itself, and our usual assumptions about size and power, they're about to get completely shattered.
We all kind of think this, right? A model with more parameters, a bigger brain, it's just got to use more energy. It makes intuitive sense. But what if that's just plain wrong?
Okay, so get this. There's something called the GPT-Neo 2.7b anomaly. It's a 2.7 billion parameter model, but on certain tasks, it used more than double the energy of models with 7 billion parameters, like Falcon and Mistral. How is that even possible? Well, it wasn't about its size, it was about its architecture. It was just inefficiently designed. The takeaway here is incredible. How a model is built can matter way more than how big it is. A smaller, poorly designed engine can be a bigger gas guzzler than a much larger but well-engineered one.
All right, so we've looked at the software engine, we've looked at the model's design. Now we're going all the way down to the deepest layer, the physical hardware, the silicon that the AI actually runs on. And this is where we find one of the most surprising and frankly powerful ways to save energy.
Now, don't let the name scare you. Dynamic Voltage and Frequency Scaling, or DVFS. All this really means is that it's a feature that lets you control exactly how fast a GPU's processor is running. Just think of it like having a manual transmission for your car's engine. You get precise control over the RPMs, and that changes everything.
And this gives us a classic trade-off. If you run the GPU at a lower clock speed, you save a ton of power, but your AI takes longer to respond. That's high latency. But if you crank up the clock speed, you get those lightning-fast answers, but your power consumption just goes through the roof. It's a constant balancing act.
So the whole point here, the big realization, is that the goal isn't just to be the fastest, and it's not to use the absolute least amount of power either. It's all about finding that perfect, elusive sweet spot, maximum efficiency. And when you find it, wow, the results are just incredible.
And guess what? Researchers actually found it. By tuning the GPU to a specific frequency right in the middle, not the fastest setting, not the slowest, they discovered they could cut energy consumption by up to 30%. And they did it with only a minimal hit to performance. It's literally the equivalent of finding that perfect cruising gear on the highway where your engine is just humming along, barely sipping any fuel. It's an absolute game changer.
So, as we start to put all these pieces together, you can see that AI efficiency isn't about one single solution. It's a really complex jigsaw puzzle with all these interconnected pieces, and every single one plays a critical role.
So we have these 3 key levers, and we have to pull them all in harmony. First, you've got the software, picking the right inference engine for the job, the drag racer or the marathon runner. Second, you have the model itself, choosing one with an efficient architecture, not just a small one. And third, the hardware, actively tuning the GPU to find that perfect, energy-saving sweet spot.
Look, the bottom line is this. There is no silver bullet. There's no single magic fix. You can't just pick the quote-unquote best engine or the smallest model and call it a day. Real, meaningful efficiency comes from intelligently configuring and optimizing the entire stack, from the silicon chip all the way up to the software layer. And all of this leaves us with one final, crucial question to think about. For years, the big race in AI has been all about scale. More data, more parameters, more raw power. But as we start to confront the very real energy costs of just talking to these things, you have to wonder, is the next great race not about building a bigger factory, but about designing one that runs with incredible, unheard-of efficiency? The future of AI might just depend on it.